Hello everyone, my name is Dongdong. It is my pleasure to talk about bidirectional LSTM-based network for fall prediction in a humanoid. This paper is co-authored by Huanzhong, Aoxue Wei, and my advisor Vikram Kapila. We are from MCRL at Tendon School of Engineering in New York University. First, let's talk about the background of this paper. In an extreme disaster environment, such as earthquakes or fires, humanoids can be deployed for rescue missions instead of human, to avoid loss of life, because humanoid is built to be as flexible as a human being. For example, Fukushima nuclear disaster happened in 2011, and working in such nuclear radiation environment is fatal to human beings. In 2015, DARPA simulated a nuclear disaster environment and held a robotics challenge to address this issue. However, even with the state-of-art robots, fall is unavoidable. Falls can occur even under small disturbance in the environment, as shown in many real-life robot examples. To maneuver through a complex environment and successfully complete assigned tasks, a biped must be equipped with the capability to quickly respond to the upcoming fall. Otherwise, it may damage objects, hurt humans, or itself. Typically, in designing a controller or humanoid, it should protect the upcoming fall first, then switch it from balanced controller to fall controller. The fall controller can try to change the direction of fall, avoid fall by stepping, or optimization or optimize its fall actions to protect itself. However, the foremost and critical part is to predict the fall early enough to allow the fall controller to have ample time to determine the next course of action. This is the topic we will discuss in the following part. Before we explain our approach, I want to introduce two important concepts to evaluate the fall prediction. The first concept is fall positive rate, which means that the fraction of trajectories in which fall is predicted for a balanced state. The predictor may make a mistake and predict the robot will fall, even when the fall will never happen. We try to reduce the fall positive rate because a larger FPR wastes time by unnecessarily switching the controller from the balanced state to fall state. Doing the fall protect action in the improper time may even cause a fall. Another concept is lead time. It measures the elapsed time between the prediction of fall and the actual fall. The desired lead time should be as long as the fall time. Once the force applied on the robot that is deemed to eventually lead to fall, the fall predictor should raise the alert. That's the ideal case. However, after the force applied on the robot, the balanced state and fall state are very similar to each other, and it is challenging to differentiate between them within a small interval by relying on instantaneous states, which is considered by previous method. Because of the complex and potentially chaotic response of biped to environmental forces, it may not be sufficient to make predictions using only the instantaneous measurements. Thus, we proceed to use recurrent neural network, specifically long short-term memory, to use a series of historical data to do fall prediction. Let's talk about the features used for training LSTM network. We consider the 6 features which will be affected by the fall. They are central mass, central pressure, linear momentum with its derivative, and angular momentum with its derivative. This slide shows the features and different force magnitudes. The red color shows the time when we applied force on the robot. There are 3 different colored trajectories in each figure. The blue curve shows the states without force. The green curve shows the balanced state and the small force. The pink curve shows the fallen state and a large force. As we can see from the figure, the 6 features contain both low and high frequency content, which matches the characteristic of LSTM neural network. The LSTM networks are proved to have the ability to model signals with low and high frequency content. Therefore, we adopt LSTM-based method for fall prediction. For the network architecture, we use the bidirectional LSTM for fall prediction. The outputs of hidden layers in the forward and backward directions are combined with two fully connected layers. To stabilize the neural network from numerical view, we apply the sigmoid function to process the output of the final layer with a linear combination. In this slide, let's talk about how we set up the training data. First, we collected the data in a standing robot for static case and a walking robot for dynamic case. For both static and dynamic cases, we applied horizontal forces on the torso of the robot with various selected magnitudes, directions, positions within the range shown in this table. For the dynamic case, since the robot is walking, the gate faces might affect the prediction performance. We added the different force application time when the robot is in different gate faces. Next, in the simulation, all the features are recorded. Finally, we divided the trajectories into two categories, namely balanced trajectory and fallen trajectory, by evaluating the center of mass position at the end of each simulation episode. In this slide, we will talk about our labeling strategy. While labeling for each dataset in LSTM, we propose to use a strategy to trade off the reduction of FPR and elongation of lead time. Instead of directly labeling the data after force application in the fallen trajectory as 1, we propose to use the above equation to label the data. In above equation, P bar is a threshold for fall prediction in the evaluation process. We label the first dataset once force applied on a fallen trajectory as P bar instead of 1. Then we gradually increase this labeling value from P bar to 1 as time passes by. The slope coefficient alpha in the labeling process will affect the final evaluation result as shown in these two figures. When the value of alpha is increased, the output of the predictor after the training will respond more quickly to the applied force, resulting in longer lead time and higher FPR. Alternatively, when alpha is decreased, the output of the predictor after the training will respond slowly to the applied force. The error of predictor in the balanced state will decrease to yield a lower FPR, and the lead time of the predictor for fallen state will become shorter. By tuning this coefficient alpha, we can balance the FPR and the lead time based on actual need of our users. We trained the neural network based on the data and evaluated the predictor for static and dynamic cases separately. For the static prediction result, we kept the robot standing on the ground with knees bent. First, we applied 3 different forces in increasing order on the robot. As we can see from the figure, our predictor can accurately predict the fallen and balanced state. After we apply the first 2 forces, the prediction signals are lower than the threshold 0.5, and the robot is in balanced state. But after the third force applied on the robot, we can see the signal exceed the threshold before the robot starts to fall down. Next, we evaluate our predictor performance by testing the predictor on 2 different datasets. One dataset uses the forces with 100 magnitudes applied at 100 different angles. The other one uses the forces with 100 different magnitudes applied at 100 different heights. We summarize the lead time and FPR in the figure and the table. The dynamic prediction result is evaluated when the robot is walking on the ground. Similar to static case, first we apply 3 different forces in increasing order on the robot. The predictor predicts the fall accurately under 3 different forces. Next, we evaluate our predictor performance by testing the predictor on 3 different datasets. Different from the static case, we added 1 more dataset with consideration to the magnitude and time. After that, we summarize our lead time, fall time, and the FPR in these 3 figures and this table. In this slide, we introduce the variants of LSTM and compare them with the fully connected neural network. As we can see from the figure, the BLSTM RNN achieved lower FPR than all other methods while maintaining a smaller variance in error. In contrast to fully connected neural network considered in prior work, the bidirectional LSTM RNN reduced the FPR from 13% to 2% while maintaining minimum impact on the lead time. In this slide, we have a video to demonstrate our result. Conclusion and contributions. In this paper, we utilize a series of historical and future states as the inputs for training and effectively predict the fall by bidirectional LSTM neural network. Also, we introduced a trade-off coefficient alpha, which allows the bidirectional LSTM recurrent neural network to choose between a lower FPR versus a longer lead time based on the task at hand. Finally, our simulation experiment showed a considerable reduction in FPR while achieving approximately a similar lead time that is produced with the use of fully connected neural network. Finally, we thank our sponsors for supporting our work: National Science Foundation, New York University, NASA New York Space Ground Consortium. Thanks for your support.